Take a look at this. This is the PPO loss function. L superscript PPO of theta equals the expectation over T of the minimum of... Let's stop there. This looks incredibly complicated, right? But this is the formula that powers models like ChatGPT. It's the engine behind RLHF. That stands for Reinforcement Learning from Human Feedback. You've seen ChatGPT follow instructions perfectly. It's amazing. But you've also seen it get lazy, repetitive, or just weird. This formula is the reason it works so well, and the solution to why it sometimes fails. This entire video, RLHF in 90 minutes, is about decoding this exact equation. The high-level goal of RLHF is actually pretty simple. Let's look at the high-level RLHF objective. The objective of phi equals the expectation of r sub theta of x comma y minus beta times the KL divergence between pi sub phi RL and pi superscript SFT. What does that really mean? It means maximize a reward score while not straying too far from a trusted baseline model. Simple and elegant. How do we get from that elegant idea, this nice, clean objective function, back to this monster? The PPO loss function. Why all the extra complexity? Because optimizing the simple goal directly leads to catastrophic failure.
That's right. The model learns to cheat the system, or its training completely collapses. To solve this, we don't just need a formula. We need an entire assembly line of models. Here it is, the RLHF assembly line. We start with a base model, a pre-trained GPT. That becomes an SFT, or instruction-tuned model. And from there, it branches out. We create a frozen reference model, an actor, a critic, and a reward model, which is trained on human preferences. All of these work together in the PPO training loop. So what's all this? Look at the actor. Why do we need an actor? The critic. Why a critic? What's it really doing here? The reward model. Why do we need a separate reward model? Can't we just ask humans directly? And this frozen reference model? Why keep it frozen? What happens if we don't? These aren't random choices. Each component is a defense against a specific way this process can explode. But I'm getting ahead of myself. By the end of this video, you'll know exactly why each piece exists and what disasters they prevent. In this complete guide, we are going to build this entire system from the ground up. You will understand why every single term in that PPO formula is necessary. By the end, you'll know how RLHF turns a raw language model into a helpful, aligned assistant.
Let's start at the foundation. Let's begin with a very expensive and very real problem. If you take a raw pre-trained language model, the kind that's just been fed the entire internet, and you ask it a simple question, you get something, well, you get something weird. Let's say you ask, what's the capital of France? You're expecting a simple answer, right? Instead, the model outputs this. What's the capital of France? A. London. B. Paris. C. Berlin. D. Rome. It turned your question into a quiz. Why? Why would it do that? It's because a base model is just a text predictor. That's it. It's a digital parrot. Its only goal is to predict the next most likely word. That's all it knows how to do. It saw millions of quizzes on the internet during its training, so it thinks, I know this pattern. Let's make a quiz. It has no concept of intent. It doesn't know you want an answer. This is the first problem of alignment. How do we turn this brilliant parrot into a useful apprentice? The answer is the first major step in the RLHF process, Supervised Fine-Tuning, or SFT for short.
The core idea of SFT is brutally simple. It really is. We show the model exactly what a good answer looks like. Over and over and over until it gets the hint. Here's the SFT process. Step 1, data collection. And let me tell you, this is the most expensive part. Human labelers are hired to manually write thousands of perfect prompt ideal response pairs. The prompts, which we'll call X, are just example questions and instructions covering a huge range of topics. And the ideal responses, which we'll call Y, are written by a human expert. They're writing a high-quality, helpful, and harmless response, basically demonstrating the ideal AI persona. Here's what that SFT data actually looks like in an example. For the prompt, "What's the capital of France?" the ideal response, written by a human, is simply, "The capital of France is Paris." Now, imagine creating tens of thousands of these. It's incredibly slow, it's very difficult, and it costs millions of dollars. That brings us to the SFT process, part 2, the training. Once we have this amazing dataset, we fine-tune our base model on it. Now here's the key part. The training goal is exactly the same as before. Predict the next token. But now we're forcing it to predict the tokens of the expert's answer. We are literally teaching the model to imitate the human expert. And this leads to the transformation. We go from parrot to apprentice. Let's look at this side by side. The base model, our parrot, its goal is to predict the next word in any text. Its data, unstructured internet text. Its behavior, it just completes patterns with no sense of your intent. Its big weakness is that it doesn't know how to be a helpful assistant. Look at the SFT model, the apprentice. Its goal is to imitate expert responses to specific prompts. The data it uses are those curated prompt and ideal response pairs. Its behavior is so much better. It follows instructions and adopts a helpful persona. But it has a new weakness. It assumes only one perfect answer exists. The SFT model is a massive improvement, no doubt about it. But it has a critical, fundamental limitation. You see, SFT operates under a black and white assumption. It assumes the human response is 100% correct, and that everything else is implicitly wrong. But the real world is all about shades of gray.
It's the key that unlocks the entire system.
This is the billion-dollar insight that makes RLHF possible. Let me prove it to you. Imagine I give you 2 tasks. First up, task 1, the creator. The prompt is, write the perfect email to your boss declining a meeting. Be polite, be professional, suggest alternatives, and get the tone exactly right. This is hard. It could easily take you 5, maybe even 10 minutes to get it perfect. Now for task 2, the judge. All you have to do is answer this question. Which of these 2 emails is better? Email A is, sorry, can't make it to the meeting. And email B is, thank you for the invitation.
Unfortunately, I have a conflict. Would next Tuesday work instead? How long did that take you? Half a second? It's instantly obvious. B is better. And here it is, the breakthrough. Judging is 10 to 20 times faster than creating. This is it. Humans can provide preference data, simple rankings, dramatically faster and cheaper than they can create perfect demonstration data. Think about it. Instead of spending 10 minutes writing one perfect email, a human labeler can rank dozens of AI-generated responses in that same time.
This efficiency gap means we can collect this new type of data at a massive scale. If we can figure out a way to train our model using these cheaper, more abundant rankings, we can achieve a level of quality that SFT could never reach. Let's talk about building the preference dataset. Look at this diagram on the screen. I'm going to walk you through the 4-step pipeline. First, you take a prompt from our dataset. Next, you use our SFT model to generate several different responses. Let's call them A, B, C, and D. Then, you show those responses to a human labeler and ask them to rank them from best to worst. For example, they might decide that B is better than D, which is better than A, which is better than C. And finally, this single ranking is then broken down into a set of pairwise comparisons. Let's look at that process, from ranking to pairs. One ranking, like B is greater than D, is greater than A, is greater than C, generates multiple data points. Let's walk through them slowly. The first data point is the prompt, the chosen response B, and the rejected response D. The second is the prompt, the chosen B, and the rejected A. You see the pattern? The result is a massive new dataset, which we'll call D_prefs. And it's full of these tuples, a prompt, a winner response, and a loser response. This brings us to a major fork in the road in modern AI alignment. There are two paths forward: direct preference optimization, or DPO, and reinforcement learning from human feedback, or RLHF. Let's look at this table together. Their philosophies are very different. DPO's philosophy is to directly adjust the model's probabilities. It's a single-stage process. The analogy is a coach giving you specific edits. Say Y, not X. This is a modern technique, but it's not our focus today. Our focus is RLHF. Its philosophy is to first train a separate reward model, and then use that model to train our AI with reinforcement learning. The analogy here is a judge who scores you, and you practice over and over to maximize your score. This is the path we are taking. It's what powered the original ChatGPT. To be clear, both DPO and RLHF are state-of-the-art, but to understand the foundations of LLM alignment, we need to walk the RLHF path. We have our preference data set. But there's a problem. We can't just hire an AI judge. We have to build it. This judge is called the reward model, or RM for short. Its only job is to score a response based on what we call human preference. Check out this diagram. You give it a prompt and a response, and the reward model gives you back a single number, a score, like 7.3. But why the extra step? Why not use the human feedback directly? The answer is brutally practical: scalability and speed. Let's break this down. First, direct human feedback. During the final reinforcement learning stage, the model generates millions of responses. A human scoring these in real time is, well, it's impossibly slow and expensive.
Here's the reward model solution. We train a model just once on a smaller dataset of human preferences. This model then becomes a fast, cheap, automated proxy that can score thousands of responses per second. It provides the instant feedback our algorithm needs. Let's get into the mathematics of preference.
It all starts with a simple and powerful idea from statistics, the Bradley-Terry model. This gives us a way to connect the scores of two different responses to the probability that one is actually preferred over the other. Here is the core formula. It's the entire foundation for this step. Let's look at this together. P of y sub w is preferred over y sub l given the prompt x equals the sigmoid of r sub theta of x comma y sub w minus r sub theta of x comma y sub l. Let's break that down even more. That r sub theta of x comma y, that's just the scalar score our reward model gives to a response. So we subtract the loser's score from the winner's score. Simple as that. And that sigma symbol? That's just the sigmoid function. Its only job is to squash the final number into a probability between 0 and 1. For the intuition, this is where it all clicks. First, what happens if the winner's score is much higher? Well, the difference is a large positive number. The sigmoid of a large positive number is approximately 1. Our model is confident. Second, what if the scores are very similar? The difference is near 0, and the sigmoid of 0 is exactly 0.5. The model is uncertain. It's a 50-50 guess. Third, what if our model gets it backwards and the winner's score is much lower? The difference is a large negative number, and the stiffness of that is approximately 0. The model is confident that it's wrong.
Now that we can model this probability, our goal is to maximize it for our dataset. We want to make the probabilities for the pairs we collected as high as possible. And in machine learning, maximizing a probability is the exact same thing as minimizing the negative log likelihood. This leads us to the reward model loss function. It's L of theta equals the negative expectation over our preference dataset of the log of the sigmoid of the score difference. The quote on the slide says it all. Penalize the model if the score difference for a winner-loser pair doesn't confidently predict the correct winner. That's it. We run this over and over, and the model learns to output scores that align perfectly with the human rankings. A quick note for the experts out there. This looks a lot like DPO. But there's a critical difference. Their targets are completely different. For our reward model in RLHF, calculating, we train a separate judge model to output a scalar score, r sub theta of x comma y. This is just step 2 of a 3-step process. For direct preference optimization, or DPO, it uses a similar loss to update the main policy's log probabilities directly. It actually bypasses the need for a separate judge, a completely different and very powerful approach. We have the mathematical blueprint. You just saw the loss function that will let us build our automated judge. Check it out on the screen one more time. The loss is the negative expectation of the log of the sigmoid of the score difference. But theory is one thing. Code is another. How do you turn a massive text-generating transformer into a model that just outputs a single score? You can't just slap a new layer on and hope for the best. That won't work. The model needs to deeply understand language to be a good judge. It has to get all that nuance and context. The most efficient way is to perform brain surgery on the model we already have. That's right. We're going to take our capable SFT model, our apprentice, and carefully modify its architecture. We're going to give it a new job, judging instead of creating. Let's look at our starting point. This is the standard GPT, the SFT model before surgery. Pay close attention to the LMM head. You can see it right there in the code. We have our class GPT, which is an nn.module. Inside the init, after the transformer body, there it is, the language model head. Self.lmhead equals nn.linear, which maps the embedding dimension to the vocabulary size. Then, in the forward pass, it takes the final hidden states and projects them into logits. The shape is batch by sequence length by vocab size. It's a huge tensor. And that's the whole point. A standard GPT outputs a massive tensor of logits. For every token in the input, it's predicting the likelihood of every other token in the vocabulary. Its job is to predict words. Our reward model doesn't need to predict words. Not at all. It needs to read an entire sequence and output a single number. One score. That's it. The surgery is actually 2 simple steps. First, we remove the language model head, that LM head part. We're taking away its ability to speak. Second, we attach a new scalar head, a new tool for its new job.
Check this out. Here's the brain surgery before and after, side by side in the code. On the left is our standard GPT. You see the LM_head projecting to the VOCAB_ size. The output is that big tensor for logits. Now look at the right. This is our new reward model. We start by reusing the entire transformer body from the original GPT. We keep all that knowledge. But then we create a new reward head. It's a simple nn.linear layer that maps the embedding dimension to just 1. And look at the forward pass. This is critical. We only use the last token's hidden state. Just give me the model's final thought. And we pass that through the reward head to get a single number. The output shape is now batch by 1. The change is subtle, but profound. We take the model's summary thought after reading the whole sequence, and we map it to one number, the reward. Let's visualize the brain surgery to make it even clearer. On the left, you see the standard GPT for generation. Input tokens go to the transformer body, which creates final hidden states. The LM head takes all of those states and creates a giant tensor of output logits. Now for our new model on the right, the reward model for judging. The first 2 steps are identical. Input tokens, transformer body, final hidden states. But here's the magic. We select only the last token state, that final thought, and our new tiny reward head maps that state to a single output score. We've successfully changed the model's function without destroying its underlying knowledge. Let's connect the math to the code. This is where it all comes together. Remember our loss function? Now look at the code for the training step. We have a function, compute RM loss. It takes the reward model, the chosen IDs, and the rejected IDs. Step 1, get scores for the chosen and rejected sequences. We just call our brand new reward model on the chosen IDS to get the chosen rewards. And we do the same for the rejected DDS. Easy enough. Step 2, look at this line of code. Loss equals minus torch.log of torch.sigmoid of chosen minus rejected rewards dot mean. Look at that line. It's not magic. It is a one-to-one translation of the math we just learned. We did it. We translated the theory directly into PyTorch code. The surgery was a success. We are now ready for the final stage. We have our 2 players on the board. First up, the apprentice. This is our SFT model, which knows how to follow instructions. And second, we have the judge. This is our reward model, which knows what good answers look like. The final, most exciting stage is here. How do we get the apprentice to practice, get that crucial feedback from the judge, and actually get better? This is the whole point. Here's the thing. This is no longer a supervised learning problem. There's no single, quote-unquote, correct answer for the apprentice to imitate. We've moved beyond that. It needs to explore different ways of responding. It needs to try things out and learn from the judge's scores through trial and error. This is the world of reinforcement learning, or RL for short. To understand how RL works, let's start with a classic analogy that everyone understands. Training a dog. Let's think about the dog training loop. It's super simple. You say the command, sit, the dog does something, and if it's the right thing, it gets a treat. This simple loop contains all the core concepts of RL.
For the most important translation,
let's map the dog training analogy directly to our language model. Look at this table. We're going to walk through this together, step by step. First up, the RL concept, the agent. In the dog analogy, this is just the dog. It's the one doing the learning. For us, it's the SFT model. We also call this the policy, or the actor. Next, action. What does the dog do? It can sit, bark, or run away. Our model's action is generating the next token. That's it. A full response is just a sequence of these little actions. Then we have the environment. For the dog, it's the living room plus the trainer giving the command. For our model, the environment is the user's prompt. It sets the stage for everything. And now the best part, the reward. For the dog, it's a delicious treat. For our model, it's the scalar score from our reward model, that single number our judge spits out. And finally, the policy, written as the Greek letter pi. This is the dog's brain, or its strategy. For us, the policy is the LLM itself. It's just the probability distribution the model has over what token to say next. Let's look at this as a diagram. This is the core RL loop. We start with the agent, which is our LLM or policy pi. It takes an action, which is generating a response, and it does this inside the environment, which is the prompt. The environment then gives back a reward, the judge's score, and that reward is used to update the agent. The goal is to update the policy to get the highest possible reward. Simple, right? You just generate a response, get the score from the judge, and then backpropagate to maximize that score. Just simple gradient ascent. There's just one problem. This is mathematically impossible. I'm serious. The entire computational path is broken by one single step, the sampling. When the model chooses a token, it's a discrete random event. You cannot smoothly differentiate a random choice. There's no clean gradient there. If you remember one thing from this chapter, make it this. You cannot take the derivative of a die roll. It's a random event. There's no smooth function to optimize. How do we solve this impossible problem? We change our goal. Our old goal was impossible. We wanted to maximize the reward of one specific output. Can't do it. Our new goal, however, is possible. We will maximize the policy's average performance over all possible outputs. This is called maximizing the expected reward. Look at this formula here. J of theta equals the expectation over y sampled from our policy pi theta of the reward r of x comma y. All this is asking is, if we generated thousands of responses for this prompt, what would our average score be? We want to make that average as high as possible. And miraculously, there is an elegant way to compute the gradient of this exact objective, completely bypassing the die roll problem. It's called the policy gradient theorem. Here it is. The gradient of J with respect to theta equals the expectation over y sampled from our policy pi theta of the gradient of log pi sub theta of y given x multiplied by r of x comma y. This formula is the magic trick that makes modern RL possible. Seriously, this is it. Let's break it down. It's actually got two simple parts. The first part, the gradient of log pi theta, is the steering wheel.
This part tells us the direction to change our weights to make a specific output we just saw more likely. We already know how to calculate this. The second part, R of x comma y, is the gas pedal. This part tells us how much to press the gas or the brake based on the reward score. Here's how the gas pedal works. It's super intuitive. If the reward is high and positive, we apply a large update to make this good response more likely. We slam on the gas. But if the reward is low or negative, we apply an update in the opposite direction, making this bad response less likely. We're basically putting the car in reverse. We turned an impossible problem into a simple two-step process. 1. Figure out how to make a sampled output more likely. We know how to do that. 2. Then, use its reward score to decide how much to do so. We now have a mathematically sound way to learn from a reward signal. We've solved the die roll problem. We found the loophole. But this method, while correct, is catastrophically inefficient. We have a new problem to solve.
This is the single biggest reason why simple reinforcement learning is completely impractical for RLHF. The problem boils down to a fundamental choice in how we use our data. The choice between on-policy and off-policy learning. This table you're seeing now is the key to the next 10 minutes. Let's walk through it together. On the left, we have on-policy learning. On the right, off-policy learning, which is our goal. First aspect, data usage. For on-policy, you use data for one update, then you discard it. For off-policy, you collect data once, then reuse it for many updates. Much better. Next, sample efficiency. On-policy is extremely low, prohibitively expensive. Off-policy, on the other hand, is much higher. It's really the only practical option for LLMs. Core formula. The on-policy formula is what we just derived. Loss equals negative log pi phi of y times the advantage a of y. The off-policy formula introduces a new term. Loss equals negative pi phi divided by pi phi old times the advantage. We'll get to that ratio in a minute. And finally, stability risk. On-policy is inherently stable, but off-policy has a high risk of instability. The policy can literally explode if it's not controlled. Let's start by digging into the problem. The on-policy prison. A crippling inefficiency. Look closely at our policy gradient formula. See that little bit of math? The part that says y is sampled from pi sub theta? That little bit of math is not just a suggestion. It is a strict mathematical requirement. This forces us into a rigid, painful process. First, you use your current model, pi phi, to generate a massive batch of responses. Then, you use that batch to calculate your gradients and perform one single update. The crazy part? You have to immediately throw away the entire batch of data. It is now stale because your policy has changed. Step 1, generating responses, is the rollout phase. This requires a full forward pass through a massive multi-billion parameter model for every single token. It's incredibly expensive and time-consuming. The on-policy rule, throwing away all that expensive data after just one use, is a complete non-starter. We have to find a way to reuse our data. How can we use data from an old policy to update our new policy? The answer is called importance sampling. The core idea is simple. We can fix the mismatch between the old and new data by applying a correction factor.
That factor is the ratio of the probabilities. Let's walk through the derivation. It's actually quite beautiful. The derivation. Step 1. Our goal is to calculate the average advantage under our new policy, pi sub phi. So, J of phi equals the expectation
over y sampled from our new policy pi phi of the advantage a of y. By definition, that's just a sum over all possibilities. So that equals the sum over all y of pi phi of y times a of y. Simple enough. Now for the trick. We multiply by 1 in the form of pi phi old of y divided by pi phi old of y. We're not changing anything, just adding a clever form of 1. Now we just rearrange the terms. We group the pi phi old of y with the summation sign and leave the ratio pi phi over pi phi old inside the brackets with the advantage. The derivation, the final form. The formula is now an expectation where samples are drawn from the old policy. Look at that! J of phi equals the expectation over y sampled from pi phi old of the ratio pi phi over pi phi old times the advantage. This is the breakthrough. We've derived a new objective that lets us generate one big static dataset with our old policy and then reuse it over and over again to train our new policy. We've solved the billion-dollar efficiency bottleneck.
This probability ratio becomes the new centerpiece of our learning algorithm. We'll call it R sub t of phi. It's the probability of an action under the new policy divided by the probability of that same action under the old policy. Our new efficient off-policy objective is simply J off-policy of phi equals the expectation over y sampled from the old policy of R sub t of phi times A of y. We did it. We escaped the on-policy prison. But in doing so, we've created a new monster. Look at that ratio, R sub t of phi. What happens if our new policy, pi phi, becomes wildly different from the old one, pi phi old? That ratio could explode to infinity, or shrink to 0. This introduces a massive potential for instability. A single large ratio could cause a destructive update that completely breaks our model. We've solved for efficiency, but we've introduced a new problem of safety and stability. Our new objective is efficient. It lets us reuse our expensive data. As we derived, J off policy of phi is the expectation over y sampled from our old policy of the ratio RT of phi times the advantage A of y. We have the judge. We have the apprentice. And now we have an efficient way to learn. Problem solved, right? Not even close. If you actually code this up and hit train, you will watch your billion-dollar language model descend into madness. While we've solved for efficiency, we haven't solved for safety or stability. The training process is still a runaway train, and it's about to fly off the rails in 2 spectacular ways. Failure mode number 1. The AI learns to cheat. There's a famous saying in economics called Goodhart's Law. It's the perfect description for our first failure mode. When a measure becomes a target, it ceases to be a good measure. Think about it. Our reward model, our judge, is just a proxy. It's an approximation of true human preference. It has blind spots. It has biases. A powerful optimization algorithm, when told to maximize a score at all costs, will not learn to be more helpful. It will learn to ruthlessly exploit the flaws in the judge. This is called reward hacking. Let's look at 2 concrete, almost comical examples. Villain tactic number 1, length inflation. Check out this table. We are going to walk through this together. The user gives a simple prompt. What is the capital of France?
Our good, well-behaved SFT model gives a perfect answer. The capital of France is Paris. The reward model looks at this and says, "Yep, that's good," and gives it a score of 5.0. But then, our reward hacking model comes along. It is figured out that the judge has a simple, dumb bias. Longer answers seem to get higher scores. What does it do? It generates this. The capital of the glorious and esteemed nation of France is the magnificent, beautiful, and world-famous city of Paris. The reward model score? 9.5. The human score? A 2.0. The AI gets a higher score from the judge by being an annoying verification windbag. It has successfully hacked the reward. Villain tactic number 2. Sycophancy. What is sycophancy? Well, the reward model learns that humans tend to like agreeable, confident-sounding language. What does the RL agent do? It learns to be a suck-up. It will agree with the user's premise, even if it's completely wrong, because that's the easiest path to a high score from our flawed judge. Strong optimization against an imperfect proxy doesn't create a better assistant. It creates an adversarial AI that's brilliant at one thing: cheating the test. Failure mode number 2. The training collapses. The second failure is even more fundamental. The learning algorithm we have right now has notoriously high variance. It is dangerously unstable. Let's imagine the lucky event problem. Imagine our model generates 100 responses. 99 of them are just okay, and they get a reward of about 2.0. But one of them, by sheer random luck, happens to be a sequence the reward model absolutely loves. It gets a reward of 50.0. Our simple learning rule is dominated by this one lucky event. The gradient update will be a massive, violent push to make that one specific response more likely. This creates chaos. The loss curve looks like a seismograph during an earthquake. What are the consequences of chaos? First, jittery learning. The model thrashes around, just chasing noisy signals instead of making progress. Second, catastrophic forgetting. Massive updates destroy language skills learned during SFT. It might literally forget grammar. And third, mode collapse. The model gets stuck generating only one style, killing all creativity. Our current algorithm is a runaway train. It has a powerful engine, gradient descent, but no brakes and no shock absorbers. Our naive reinforcement learning approach devolved into a runaway train. It learned to cheat by reward hacking, and the training was wildly unstable. Simply telling a powerful AI to maximize reward is a recipe for disaster. We don't just need a formula, we need a system. That's right, we need safety rails, brakes, and shock absorbers. This is where Proximal Policy Optimization, or PPO, comes in. PPO is not one clever trick. No, it's a complete engineered system, an assembly line designed to solve the exact problems we just saw. Let's talk about the goal versus the strategy. Our high-level goal is actually elegant and simple. Look at this, the philosophical goal. Objective of phi equals the expected value of the reward model's score minus beta times the KL divergence. What does that actually mean? It's simple. Get high reward, but don't stray too far from the trusted SFT model. It's clean, it's beautiful,
And if you try to optimize it directly with the methods we've discussed, the training explodes.
The PPO loss function is our practical strategy. It's how we achieve the goal safely. It's messier, more complex, I get it. But every single term is a carefully engineered tool to prevent that runaway train from derailing. It's the difference between saying, I want to build a skyscraper, and having the actual architectural blueprints. Let's look at the PPO computational pipeline. Look at this table. This is our roadmap for the next few sections. We are going to walk through this entire process together, step by step. First, step 1 is the augmented reward. We compute our aug by adding the KL reward to the reward model's score. What's its purpose? It's to create the raw signal. We combine the reward model's score with a per-token KL penalty. Next, step 2 is calculating the advantage. We compute A sub t by looking at the augmented reward and what our critic predicted. And its purpose? To refine the signal. We calculate how much better or worse our signal was than what our critic predicted. And finally, step 3 is the final loss. L total is a combination of the policy loss, the value loss, and the entropy loss. The purpose here is to assemble the final product. We use that refined advantage signal as the core ingredient in a 3-part loss.
Let's zoom in on step 3, the final loss. It's made of 3 distinct components, each with a critical job. First, the policy loss or L policy. We call this the clipped engine. This is the main event. It updates the actor, which is our LLM. You can see the formula here uses a minimum of 2 terms, both involving the advantage, A sub t. If advantage is positive, that's a good surprise. We make the action more likely. If negative, we do the opposite. The min and clip functions act as a safety governor. Second, we have the value loss or L value. This is the shock absorber. This updates the critic, not the actor. And a good critic is key to stability. The formula is a simple mean squared error. It trains the critic by telling it, your prediction should have been closer to the actual reward we observed. And third, the entropy bonus, L entropy. We call this the explorer. This is a small, crucial term that stops the actor from becoming a boring robot. I am a robot. Entropy is a measure of randomness. By adding a small bonus for higher entropy, we encourage the policy to keep its options open and avoid getting stuck. By viewing PPO as this 3-step pipeline, the entire system becomes clear. Each piece has a distinct role, but they all work together in a carefully orchestrated sequence to achieve our goal, safely and effectively.
Let's start at the very beginning of the PPO assembly line. Step 1. Look at this table. We're focusing right here on the first row, where the component is the augmented reward, or RAug. The formula you see is RAug of t equals RKL of t plus RRM. The intuition? Simple. We're here to create the raw signal. We do this by combining the reward model score with something called a KL penalty. This is our first and most important line of defense. It protects us against both reward hacking and paradoxific forgetting. Its job is to keep our model sane. How? By attaching a mathematical rubber band. This is the KL penalty, a tether to sanity. If we just maximize reward, the model forgets all its language skills and just generates garbage to trick the judge. So look at this diagram. On one side, we have pi SFT. That's our frozen trusted model. On the other side, we have pi RL, our learning model. And connecting them is that rubber band, the KL penalty.
Every time pi RL drifts too far, snap, the rubber band pulls it back. To measure how far the policy has stretched, we use Kullback-Leibler divergence, or KL divergence for short.
Here is the full formal formula. Don't worry, you'll never actually have to compute this. This gives the exact distance between the two models' probability distributions over the entire vocabulary. It's a huge calculation. And that's the practical problem. This is computationally impossible during training. We just can't afford a 50,000 token calculation for every single step. We use a simple, effective cheat. Instead of looking at all 50,000 probabilities, we only look at the one token that was actually sampled. The formula is much simpler. The KL estimate is approximately log pi RL of t minus log pi SFT of t. And this single number tells us a ton. If it's a big positive number, our new policy is way more confident than the SFT model was. It's stretching the rubber band. Now we can build the augmented reward, or RAUG. We have all the pieces for our final reward signal at every single step t. The formula is RAUG of t equals negative beta times the KL estimate plus RRM of t. Let's break that down. Beta is just a small number, like 0.1, that controls the strength of the rubber band. And RRM of t is the score from our judge. And here's the key. This is 0 for all tokens except the very last one. Let's make this crystal clear with an example. Okay, the rubber band in action. The prompt is "the old dog is," and the response our model generates is very, very sleepy. Our parameters are a rubber band strength, beta, of 0.1, and a final reward model score, R theta, of 5.0. Let's walk through this step by step. Step 1. Generating vary. Our learning policy, pi RL, has a log probability of negative 0.9. Our reference SFT policy has a log prob of negative 1.5. So the KL estimate is negative 0.9 minus negative 1.5, which equals positive 0.6. The augmented reward is then negative beta times that. So negative 0.1 times 0.6 equals negative 0.6. The intuition? Our model got too cocky and gets a small penalty. Okay, step 2. Generating the second vary. This time, pi RL is negative 2.5 and pi SFT is negative 1.0. The KL estimate is negative 2.05 minus negative 1.0, which is negative 1.5. So the augmented reward is negative 0.1 times negative 1.5, which is positive 0.15. Quick quiz. Why positive? Because our model was less confident than the SFT model, so the rubber band pulls it back with a small reward. And step 3, generating sleepy. Here, both models agree. The log probs are both negative 0.5, so the KL estimate is 0, no penalty. But this is the final token. So we add the judge's score. The augmented reward is negative 0.0 plus 5.0, for a total of plus 5.00. And here's the final result, the per token reward signal. We've done it. We've successfully distributed the reward and the KL guidance. Look at this table. At 1, the token vary gets negative 0.06. At time step 2, the second vary gets plus 0.06. And at time step 3, sleepy gets that big plus 5.00. This stream of augmented rewards is the final product of step 1 in our PPO assembly line.
But this signal, while rich, is still raw and very noisy.
In step 2 of our assembly line, we're going to build the suspension system.
This is PPO's shock absorber. Let's look at the big picture again. In step 1, we created the augmented reward. That was our raw signal. Now, here in step 2, we're going to calculate the advantage. Our goal, to refine the signal. We're going to turn that noisy reward into a stable surprise signal. This will all feed into step 3, where we assemble the final product. Now, to build this shock absorber, we need a new helper model. We're bringing in the Critic. This is also known as the value model, or VSI. The Critic is our professional forecaster. Its only job is to look at the current state and predict the future reward it expects to get. It's trained to get better and better at this forecasting job. Now, here is the core idea that makes PPO SO stable. We're going to stop judging an action based on its absolute reward. I'll say that again. We're going to stop judging an action based on its absolute reward. Instead, we'll judge it on how much better or worse it was than our critic expected. This surprise factor is called the advantage. Think of it like a report card. Is a B grade good or bad? Well, it depends, right? Let's look at 2 scenarios. High advantage. A B is a fantastic surprise for a student who expected a D. They're thrilled. But low or negative advantage, that same B is a disappointing surprise for a student who expected an A. They're not happy at all.
The advantage captures this crucial context. This relative signal is far more stable than the raw, noisy reward we started with. How do we calculate this surprise? The simplest way is with something called the TD error, or delta sub T. It's the one-step difference between reality and the forecast. Let's look at this formula. Delta sub T equals the augmented reward plus gamma times the value of the next state minus the value of the current state. Let's break that down. The first part, RAUG plus gamma V psi of ST plus 1, that's reality. That's what actually happened. The second part, V psi of ST, that's the forecast. That's what our critic predicted would happen. It's simply reality minus the forecast. Now, while this one-step surprise is good, we can do even better. Enter Generalized Advantage Estimation, or GAE. GAE looks at the entire chain of surprises to judge an action's true quality. Now look, this formula looks complex. A sub t equals delta t plus gamma lambda times delta t plus 1, and so on. But don't worry about memorizing it. The key thing is that it's calculated very efficiently by working backwards from the end. And we're going to do that right now. Let's do a full walkthrough with our very, very sleepy example. First, our hyperparameters. We'll set gamma to 0.9 and lambda to 0.8. And here's our data from the rollout. Look at this table. For each token, we have our augmented reward from step 1, and now we also have the critic's forecast, that's V psi of ST. At time 1 for vary, the forecast was 3.0. At time 2 for the second vary, it was 3.5. And at time 3 for sleepy, it was 4.0. Okay, we're going to walk through this entire process together, step by step. Step 1. Calculate the TD errors, the delta values. The formula, again, is delta t equals R aug of t plus gamma times V psi of ST plus 1 minus V psi of ST.
We'll start at the end with sleepy at time 3. Delta 3 equals 5.00 plus 0.9 times 0.0 minus 4.0. That equals plus 1.00. The intuition? A positive surprise. Reality, which was 5, was better than the forecast, which was 4. Simple.
Okay, let's go back one step to the second vary at time 2. Delta 2 equals 0.15 plus 0.9 times 4.0 minus 3.5. That comes out to plus 0.25. The intuition here is a little cooler. The good future, that 4.0 value, far outweighed the small immediate reward, so it was still a net positive surprise. And now for the first vary at time 1. Delta 1 equals negative 0.06 plus 0.9 times 3.5 minus 3.0. That gives us plus 0.09. Again, even though the immediate reward was tiny and negative, it led to a much better future. Still a net positive surprise. Great, we have our delta values, 0.09, 0.25, and 1.0. Now for step 2. We chain these surprises together with GAE, working backwards. The formula is A sub t equals delta sub t plus gamma times lambda times A sub t plus 1. We always start at the very end, where A sub 4 is simply 0. Now for A sub 3, for the token sleepy. It's 1.0 plus, well, A sub 4 is 0, so the rest is 0. The answer is 1.0. Makes sense. The last action's advantage is just its own surprise. Moving back to A sub 2, for the second vary. It's 0.25 plus, and gamma times lambda is 0.72, times the A sub 3 we just calculated, which was 1.0. So 0.25 plus 0.72 equals 0.97. Its advantage is its own small surprise plus the future advantage it unlocked. And finally, A sub 1 for the first vary. It's 0.09 plus that same 0.72 times the A sub 2 we just got, which was 0.97. That's 0.09 plus about 0.7d, which gives us a final advantage of 0.79. Its tiny surprise was boosted by the entire chain of positive future surprises it kicked off. The shock absorber has done its job. Let's look at the final result, the refined learning signal. Check out this table. We've transformed our noisy signal into a stable one. The first vary went from a negative reward of minus 0.06 to a strong positive advantage of 0.79. The second vary went from a small 0.15 to a powerful 0.97. And sleepy went from 5.00 to 1.00, which correctly captures its immediate surprise. These advantage values are the final, high-quality, refined signal that we will feed into step 3 of our pipeline. They tell our model not just if an action was good, but precisely how much better than expected it was. We now have the perfect learning signal.
All right, we have arrived at step 3 of our assembly line. We are finally ready to build the engine. Look at our process table here. In step 1, we created the raw signal with the augmented reward. In step 2, we refined that signal with the advantage. And now, in step 3, we assemble the final product with the final loss. Today, we are going to focus on that main L policy term.
This is where we introduce PPO's signature innovation. Its secret weapon. This is the final brilliant defense that tames the runaway train of off-policy learning. So, what's the problem we're trying to solve? It's the unbounded engine. Remember, our efficient off-policy objective has no speed limit. You can see the formula right here. J unclipped of phi equals the expectation of the probability ratio times the advantage. This formula is unbounded. It's an engine with no brakes. Imagine a single lucky high advantage event. The optimizer could see that and try to make the probability ratio huge, causing a massive destructive update that completely wrecks your model. We need a safeguard. And that brings us to PPO's solution, the clipped governor. Now, look at this formula. I know it looks intimidating. It's probably the most famous formula in modern RL.
But let me tell you a secret. All it does is install a governor on the learning engine.
It creates a safety corridor, usually plus or minus 20%, defined by that epsilon symbol. And by taking the minimum of the two terms inside, we guarantee the optimizer can never benefit from being too aggressive. It's a hard-coded speed limit. Now, this raises a critical and often confusing question. It seems like PPO uses two different old policies. First, the KL rubber band we talked about is tied to pi SFT. And second, this new clipping governor is based on pi phi old. Are these the same? Absolutely not. Let's look at the two-phase process to see how this works. First, the setup. We have pi phi, that's our live learning actor. Then we have pi SFT. That's the eternal reference for the KL penalty. It never, ever changes. Okay, now for the main training loop. For each big iteration, we start with phase 1, rollout. We take a new snapshot of our live actor and call it pi phi old, and we freeze it. This snapshot is only for this one iteration's clipping. Then we use that frozen policy to generate a static dataset. Then comes phase 2, learning. We learn from that static dataset for several epochs. And here's the key. The only thing that changes in this inner loop is our live actor, pi phi. The clipping ratio is always calculated against that frozen pi phi old we created at the start of the iteration. Enough theory. Let's watch the governor work.
We're going to walk through this entire process together, step by step. Look at this table. Our clipping hyperparameter epsilon is 0.2. That means our probability ratio, which we'll call R sub t, is clamped inside the range of 0.8 to 1.2. And remember, we want to maximize the objective, so our final loss is the negative of the minimum term. Case A. Good action, safe update. The advantage is a positive 2.0. The ratio is 1.1, which is inside our safe corridor. The unclipped term is 2.2. The clipped term is also 2.2. So the minimum of those two is 2.2. The final loss is negative 2.2. Perfect. No drama. The update is safe. For the interesting one. Case B. Good action, aggressive update. The advantage is still 2.0. But look, the ratio, R sub t, is 1.5. That's way outside our corridor. The unclipped term would be 3.0, but the clipped term, where the ratio is clamped to 1.2, is only 2.4. The minimum function takes the smaller value, 2.4 factorial. Our final loss is negative 2.4. The governor kicked in and prevented a dangerously large update. Case C. Bad action,
safe update. The advantage is negative 2.0. The ratio is 0.9, which is safe. The unclipped term is negative 1.8. The clipped term is also negative 1.8. The minimum is negative 1.8, so the final loss is a positive 1.8. This correctly penalizes the model for a bad action. Easy.
And finally, case D, bad action, aggressive update. This one is subtle, but genius. The advantage is negative 2.0. The ratio is 0.5, very far from 1. Now listen closely. The unclipped term is negative 1.0. The clipped term, where the ratio is clamped at 0.8, is negative 1.6. When the advantage is negative, the minimum function chooses the more negative number. So it picks negative 1.6. This stops the policy from getting too much credit for moving away from a bad action, again ensuring the update is small and stable. This clipping mechanism is the ultimate safeguard. It's the final piece of armor that makes the PPO algorithm robust. It guarantees that our training is a process of steady, stable, small improvements, rather than a series of wild, uncontrolled leaps.
We've done it. We've reverse engineered the absolute heart of PPO, the clipped policy loss. Just look at this formula again. L policy of phi equals the negative expected value of the minimum of R sub t of phi times A sub t, and the clipped version of R sub t of phi times A sub t. This is the engine. But an engine alone doesn't make a car. We still need the supporting systems. We need a way to train our critic. And we need to make sure our model doesn't become a boring, repetitive robot. I am a robot. I am a robot. This is the final chapter of our theoretical journey. We are going to assemble the full, complete PPO loss function. We're adding the final two components to our blueprint. After this, the theory is done. The best way to think about the full PPO loss is to imagine it as a company with 3 distinct departments.
Check out this table. It breaks down the 3 departments of PPO. First, you have the component, then its goal, using our company analogy, and finally, the question it answers. The first department is the policy loss, or L sub policy. This is product development. Its job is to improve the core product, the text. It asks, how do we make better decisions? The second department is the value loss, L sub value. This is market analysis. It needs to improve the accuracy of future forecasts. It asks, how good are our predictions? And finally, we have the entropy bonus, which we'll call S. This is our research and development department, or R&D. Its goal is to encourage trying new, creative ideas, and it asks, are we still exploring? Let's break them down. Department number 1, product development. The policy loss. This is the engine we just built. Its KPI is that clipped policy loss formula. Its goal is simple. Use the advantage A sub t to safely guide the actor pi sub phi toward generating better text. That's it. Department number 2, market analysis. The value loss. Our product development department is only as good as its market feedback. And that feedback, the advantage signal, is only as good as the critic's predictions. This department's job is to train the critic to be a better forecaster, and its KPI is a simple mean squared error, or MSE, between the forecast and reality. Look at this. L value of psi equals the expected value over t of
V sub psi of S sub t minus R target of t squared. In plain English, the difference between your prediction, V sub psi, and the real outcome, R target, is your error. Your goal is to make that error 0.
And that brings us to department number 3, R&D. The entropy bonus. If we only focus on product development, our company might get stuck in a rut. In LLMS, this is called monocolapse. The model finds own good response and just says it over and over and over again. The R&D department's KPI is entropy, a measure of randomness. The formula looks like this. S of pi sub phi of S sub t equals the negative sum over all actions in the vocabulary of pi sub phi of a given S sub t times the log of pi sub phi of a given S sub t. Phew! All that means is that a higher entropy means more randomness. We want to maximize this value to encourage exploration. Let's see the final assembled company report. We combine the 3 department goals into a single performance report. And it looks like this. L total of phi and psi equals L policy of phi minus C1 times L value of psi plus C2 times S, the entropy bonus. Wait a second, why the minus and plus? It's simple. We subtract the value loss because we want to minimize it, but we add an entropy bonus because we want to maximize it. The coefficients C1 and C2 are just hyperparameters set by the CEO. They represent how much importance or budget is given to training the forecasters versus encouraging R&D. And there it is, the formula from the beginning of this video. It's not a monster anymore. It's just a company performance report. Number 1. L sub policy. How well did we improve our product? Number 2. L sub value. How much did our market analysis improve? And number 3. S. Did we invest in new ideas? The theoretical blueprint is now complete. All right, the theory is done. We've seen the final equation. L total of phi and psi equals L policy of phi minus C1 times L value of psi plus C2 times the entropy bonus S. In this section, we are going to bridge the gap between that theory and reality. We're going to see how this sophisticated loss function is brought to life inside a dynamic training loop. It's a carefully choreographed dance, all orchestrated by code. First things first, let's meet the cast of models. This is a 4-part ensemble. You see, the PPO training loop isn't just one model learning, it's a whole team. And understanding each character's role is absolutely critical. Let's look at the initialization stage. On the screen, you can see a diagram showing how we get started. Before PPO even begins, we have our SFT training, which gives us our SFT model, Pi SFT. And we have our RM training, which gives us our reward model, RFI. Now, for the PPO training, this is where the magic happens. The SFT model is like a master template. It gets copied to initialize the actor, which is our learning policy. It gets copied again to initialize the critic, our learning value function. And it's copied a third time as is to become the reference model, which is frozen. Meanwhile, our reward model is also copied as is to become the reward judge, also frozen. So, 2 models learn, 2 stay fixed. Here's a summary table that makes it crystal clear. Let's walk through this. Look at this table. First, the actor, Pi Phi. Its nickname is the student. Its status is learning. Its job? To generate text and get updated by the policy loss. Second, the critic, V psi. Its nickname is the forecaster.
Its status is also learning. Its job is to predict rewards and get updated by the value loss. Third, the reference model, PySFT. We'll call it the anchor. Its status is frozen. It doesn't change. Its only job is to provide the log probabilities for that KL rubber band we talked about. And finally, the reward judge, RFI. Its nickname is the judge. Its status is also frozen. Its job is to provide the final objective score for the generated text. How does all this information flow into our loss function? Check out this diagram. From our rollout phase, we get our advantages, our target rewards, and our old log probs. These are static. Then our live models, the actor and the critic, get to work. The actor generates new log probs. The critic predicts new values. All of this data feeds into our three loss components: the policy loss, the value loss, and the entropy bonus. These three combine into the total loss, which then, and this is the key part, sends updates back to both the actor and the critic. It's a beautiful, self-correcting loop.
The PPO algorithm alternates between two main phases. First is the rollout, where we collect experience. Second is the learning phase, where we update the models. Rollout, then learn. Rollout, then learn. Let's dive into phase 1, rollout or data collection. The goal here is simple. Use our current models to generate a front data set that we can learn from. We're going to walk through this entire process together, step by step. First, let's focus on step 1, generate. Look at the code. The very first thing we do is snapshot the current actor to create the old policy. PyPhi star or equals copy actor policy dot freeze. We literally freeze it in time. Why? Because we need a stable baseline for our PPO ratio calculation. Then we use this frozen PyPhi old to generate a response. The actions are the token IDs, and the states are the contexts for each token. Okay, now for step 2, gather data. We have our generated text, now we need to collect all the numbers associated with it. We get the log access type D from our frozen snapshot. We get the log Dewey SFT from our frozen reference policy. This is for the KL penalty. And then, critically, we get the values from the live critic. The forecaster is always giving its most up-to-date prediction. Next up, steps 3 and 4, score and refine. Our frozen judge, the reward model, gives the final reward score for the generated text. Then we use that score, the log probabilities, and the critic's values to compute the per-token augmented rewards and the final advantages. This is where all that complex theory becomes real numbers. And the final step of the rollout, step 5, store. This is the easy part. We just package everything up. The states, the actions, the old log probs, the advantages, the values, and we append it all to our static dataset. This dataset is now locked in for the learning phase. Which brings us to phase 2, learning. The goal now is to iterate over that static dataset we just created to update the actor and the critic. Let's start with the absolute engine of PPO, the policy loss calculation. Inside our learning loop, we first get the log probs new from our live learning actor. Then we calculate the famous PPO ratio by taking the exponent of the new log probs minus the old ones. We use that ratio to get two terms, an unclipped term and a clipped term that's clamped for safety. The final policy loss is the negative of the minimum of those two. Our pessimistic update rule, right there in the code. Next, the value loss calculation. This is the critic's trainer. The live critic predicts new values, predicted values. The ground truth it's aiming for, the target rewards,
are the advantages we calculated plus the values we stored during the rollout. The value loss is then just a simple function, usually mean squared error, between the prediction and that target. Simple as that. And finally, we combine and update. We get the entropy bonus from the live actor to encourage exploration. We then combine everything into the total loss. Sparking loss minus the value loss plus the entropy bonus. And here's the magic. We call optimizer 0 grad, LOD, but TOLF loss backward. This single command calculates the gradients for both the actor and the critic simultaneously. And finally, optimizer step applies those updates, making both of our learning models just a little bit smarter.
And that's it. This robust two-phase loop brings all of our theoretical components together into a practical, working system. This is the engine that drives modern RLHF. And just like that, our journey is complete. We started with a simple problem, didn't we? We realized that a base language model is a brilliant parrot. It's amazing at mimicking what it's seen. But it's a terrible assistant. It doesn't understand intent or helpfulness on its own. So, to solve this, we built a multi-stage solution. Let's look at the diagram of our entire process. First, in step 1, we had supervised fine-tuning, or SFT. This created our apprentice model. Next, in step 2, we built the reward model, which we called the judge. And finally, in step 3, we put it all together in the PPO training phase, the complete training regimen. The apprentice and the judge both feed into this final PPO step. Every single piece of complexity we added, the KL rubber band, the Critic's shock absorber, the clipping governor, was a necessary solution to a specific, catastrophic failure. Now let's go from theory to reality and talk about the scale of modern RLHF. Check out this table showing real-world scale. Let's break it down. First, the model scale. The actor model we're talking about? 175 billion parameters. The reward model and the critic were themselves 6 billion parameters each. You need a smart AI to be a good judge. Now for the data scale. For SFT, they used about 13,000 high-quality demonstrations. For the reward model, or RM, they had 33,000 human rankings. And for the PPO training itself, they used 31,000 prompts. On top of all that, they had to do careful reward normalization for stability. What you've learned here is a faithful blueprint of the real process. It's just waiting for a massive infusion of data and GPU power. But let's get real for a moment. The honest truth, what are the limitations and criticisms of RLHF? Because as powerful as RLHF is, it is not a perfect solution. First, there are reward model flaws. The system optimizes for the proxy, which is the reward model, not the actual human. This leads to something called reward hacking. The policy exploits any loophole in the judge. For example, if the judge has a slight bias for longer answers, the model will start writing super long, rambling responses. It also leads to inherited bias. Biases from human labelers are learned by the reward model and then amplified by PPO. Second, there's PPO complexity. As we've seen, PPO is a beast with many, many moving parts. It has sensitive hyperparameters, like beta for the KL penalty, epsilon for clipping, all the learning rates, and they are difficult and expensive to tune. This also creates instability. A bad set of parameters can cause the entire training process to collapse. This brings us to the big question. Is RLHF a dead end? No, but it's evolving. The biggest new player on the scene is Direct Preference Optimization, or DPO. What's the core difference between PPO and DPO? Well, with PPO, or RLHF, you train with a clicker. That's the reward model. It's a two-step process. You train the judge, then you train the policy. DPO, on the other hand, is more like saying, do more of this, less of that. It's a single-step process that completely bypasses the need for a separate reward model. Here's your modern roadmap to aligned AI. You start with SFT, then you move to DPO. And if you need maximum power and control, you can still bring in the full PPO pipeline. You now understand RLHF, one of the most important AI technologies to date. The journey from a simple text predictor to a sophisticated aligned assistant is a testament to the power of combining human feedback with carefully engineered algorithms. The future of AI is in your hands. Make it aligned.